In order to test these different approaches, we use a benchmark problem, the optimization of a Pancharatnam-Berry type structure. For the just as a to refresh your memory, in the Pancharatnam-Berry type structures, we have these rectangular shapes which convert circular polarization into the other circular polarization, so they act as a half-wave plate, and we can then control the phase of the converted polarization using the angle. So we, in principle, for this system already know what the optimal solution will be like. We designed these structures in 32 different phase levels. This is an arbitrary choice for the benchmark problem here. We keep their unit cell size and height fixed. As a material set, we choose titanium dioxide on glass, and the wavelength is 633 nanometer. The unit cell is 430 nanometer in size, and we solve this design challenge using different algorithms. As a base case, a brute force parameter sweep of these three parameters, using particle swarm optimization, genetic algorithm, differential evolution, covariance matrix adaptation strategy, and Bayesian optimization. I won't run in detail through each of these. We used a standard implementation to be found in various libraries, both for the particle swarm, for the Bayesian optimization, which allows us also to get a good estimate, a polynomial approximation over the error landscape, the genetic and differential evolution algorithms, which start from a population that then evolves and over time, and the covariance matrix adaptation strategy. Now, if we take an agnostic approach, we don't have any preference for one algorithm over the other, except for what gives us the best result and what produces that result the fastest. If we compare these methods over 5 average runs, we see that all of them take several hundred iterations in order to converge, but they converge to different levels. And if we, here as a target function, we put how close in the complex plane the solution gets to our ideal solution, which is a fixed phase value within 32-step intervals with 100% polarization conversion efficiency. We see that the Bayesian algorithm and the particle swarm algorithm produce the lowest final error, that means the best structure in the end, in a typical convergence time of around 500 solver calls to converge. So that means we need to run for these 32 structures 32 times 500 solver calls to find them all. Another important algorithm that is widely used is the adjoint optimization method. The adjoint optimization method does not start from a parametrized structure, but rather produces a gradient, which can then be used in a simple gradient descent algorithm to get closer and closer to the target function. It converges significantly faster, as you can see here, roughly in about 100 calls, but there is an additional cost that each optimization loop now requires 2 full wave solution calls, one to get the forward simulation and one to get the adjoint simulation. Nonetheless, this algorithm then takes only about half the number of calls to reach an error that is on par or even below the one that was found in the Bayesian optimization. So this is a very good candidate algorithm. We see that 400 to 200 calls from the solver is what we need to find a good solution. Now let's get to the second part of how can we speed up the individual solver calls. And to do this, our approach has been to replace the full wave solution. It doesn't actually matter which type of full wave algorithm you use here, using a neural network which acts as a surrogate solver, that if we have sufficient data and sufficiently well sampled data, we can use that to predict the transmitted phase amplitude and reflected phase and amplitude for the fundamental order, which is the one we are interested in here, over a certain spectrum. And after we train that network, we see here the results both for transmission and reflection in amplitude and phase. We have the same similar reference system as before, titanium dioxide pillars on a glass substrate, and we train this network to have an as low as possible square error as well throughout the different configurations. And we see that if we use sufficient data in a sufficiently complex network, we can get the prediction accuracy within 1% of the RCWA, which is considered the ground truth in this experiment. Of course, we studied the effect of the different network architectures. We find that as we increase the number of layers and the number of neurons per layer, the error, the square error goes down up to a certain point where overfitting starts to occur. We've also optimized this over different sets of network architectures using fully connected layers or shared layers, neural tensor layers, optimize all of that. Finally, we find that we need about, and I'm sorry this dropped off the presentation here, around 140,000 RCWA pre-generated data points in order to reconstruct this neural network. And what's important is that this needs to be a representative sampling of our solution space. So we can get a neural network that produces good results if we feed in a significant amount of training data first. But once we do that, is it then faster? Well, the answer is yes, a lot faster. If we look here at this curve comparing in red the calculation time needed per number of solver calls using RCWA, and in blue the time that's needed in seconds. By the way, this is a log scale using the neural network. We see that even for a single call, once the network has been trained, it is 33 times faster. And what's more significant even is that this algorithm scales much better when we use large batches of structures calculated in parallel. In those cases, it's even 10,000 to 20,000 times faster if we call 9,000 structures in parallel. And this we can use now to combine with our genetic algorithm and find solutions like we did before in around 400 calls, but do this now much quicker. If we do a naive implementation, we just take the optimization algorithm as is and use the surrogate solver instead of the RCWA solver, we find a structure within 31 seconds. If we take advantage of the fact that we can now calculate large batches very quickly and optimize our optimization strategy for that as well, we can even find solutions within less than 5 seconds. This usually goes well, so you see here on the left-hand side a successful optimization where the green curves indicate the different trial solutions, and then the blue and red dot, which are here coinciding, represent the found target solution using the neural network and the actual target requirement that we put in. But here on the right, we see occasionally the solver will fail. In fact, the optimization algorithm does converge to the target solution, but due to remaining errors which occasionally occur in the neural network, the final solution is off when confirmed in RCWA versus the target solution. And that brings